Okay, so we have seen some man-made explosions being carried out on Earth, but much more powerful explosions take place in our galaxy and elsewhere in the universe in other distant galaxies. There are past supernovae in our own Milky Way galaxy, which have been recorded by amateur astronomers and sky watchers over millennia. And I have referred to the Crab supernova of 1054, which were recorded by the Chinese. Now, there is a coincidence that many of the positions of the supernovae are actually very close or on the galactic plane itself. The galaxy, as you know, is a spiral-shaped object with most of the massive stars happening close to the plane of the galaxy. And supernovae take place from stars which are heavier than roughly 3 solar mass or 3 times the mass of the Sun. And they are found to be in or near the spiral arms. And stars heavier than 8 solar mass are thought to lead to a different class of supernovae, which we have referred to before as the core collapse supernovae. And the reason that they occur so close to the galactic plane is that they are, in being massive stars, they are very young. Massive stars live actually much shorter time than low mass stars, and in this time the progenitor star, the parent star, didn't have enough time to move away from their place of birth, and most of the stars are actually born in the galactic plane. And so when they exploded after a few million years after they were born, they were in fact fairly close to the galactic plane. And this blue region is the galactic plane region shown in a plot of right ascension and declination. And the middle region, which is there in red, are parts of Virgo and other clusters of galaxies which are close by, Coma cluster, and some supernovae are also seen in those places, but they are very distant supernovae. Next slide. Next slide shows different types of supernovae. I have referred to earlier thermonuclear supernovae and core collapse supernovae. They are actually classified by astronomers on the basis of spectrum, optical spectrum, recorded at the time of maximum light. And the primary distinctive characteristic between the two classes is whether or not you see hydrogen in their spectrum at maximum light. If you don't see any hydrogen, they are they were originally classified as type 1 supernovae. But as time went on, the type 1 supernovae themselves got reclassified into several subclasses, 1A, 1Bs and 1Cs, which are again distinguished whether or not you see a particular silicon 2 absorption line there or not. If you don't see, if you do see an absorption trough at about 6150 angstroms, you classify this supernova as 1A, and these are the original thermonuclear supernovae, which was originally classified as simply type 1 supernovae. They have now been reclassified as 1A supernovae. If you do see hydrogen in its spectra at maximum light, then they are classified as type 2s, and type 2s were the original classification of the core collapse supernovae. But later on, from a study of the positions of 1Bs and C supernovae, in the types of galaxies that they occur, or how close to the spiral arms they are, they were also classified as belonging to the core collapse class. Next slide. Okay, so the core collapse supernovae, which we will be concentrating on in this talk, result from collapse of iron cores inside massive stars of mass usually greater than 8 solar mass. They lead to neutron stars or black holes as compact stellar remnants. A subset of the core collapse supernovae of type 1Cs, which I have showed in the previous slide just now, have been found in some cases to be associated with long duration gamma ray bursts. For example, there was a gamma ray burst called GRB 980425, which took place in 1998, April 25, and it was eventually found to be coincident with a supernova, which was called Supernova 1998 BW. So the GRBs are often associated with, or at least a class of GRBs are associated with a core collapse supernova. Normally, a typical supernova would show a non-relativistic outflow of its outermost layers, as seen by the radio emission, which is of a non-thermal nature from the supernova, whereas a GRB outflow is initially highly relativistic, and this is believed to be powered by a separate source, which is separate from the blast wave which is ripping through the star. It is believed that the GRBs are actually powered by a central engine, which could be a fast rotating neutron star or a black hole accreting mass and sending out a jet of material or jet of electromagnetic radiation.